So thanks for the opportunity to present my work here. So I have changed my title a little bit. So it's like Generalized Hydrodynamic Description of Quantum Dynamics of Expanding Free Fermionic Gas. So this is based on the two works. So one's published in PRL 2024 and one is under preparation. So let's see the setup. So we have a finite system of LS sites and it is coupled with a reservoir of infinite, it has infinite sites, and there is a defect and the coupling between the system and the reservoir has a defect, and the system is filled with fermions and the reservoir is empty. And this is the setup, and we can write down the Hamiltonian for the setup in this way. So here this Hij, the small Hij, this is the single particle Hamiltonian for this the setup, and the Ci dagger Cj, these are the fermionic creation annihilation operator. And the single particle Hamiltonian has this form where the small g is the nearest neighbor hopping, and we can design different kind of point defect changing this coupling parameter Gc. So for conformal defect, we can choose this elements of this single particle Hamiltonian like this. For hopping defect, you can choose like this, and for the density defect, we can choose this the small h elements like this. And the reason for choosing different kind of defects is that, so in the LS tends to infinity limit, this is nothing but a problem of like scattering of plane waves. And you can see for conformal defect, if we solve this, the reflection probability or the transmission probability is k independent, k is the wave vector. So for the conformal defect, whereas for the density and hopping defect, this reflection probability, this is k dependent. Now we have this setup. We want to study the dynamics of various observables using two ways. One is the exact microscopics, that is the numerics, exact numerics. So for that we need the finite dimensional Hamiltonian. So this is the Hamiltonian. Now we cannot choose the bath to be infinity. We are choosing some bath has some sites, LR number of sites, which is much larger than the system size. And we'll study the correlation matrix, evolution of the two-point correlation matrix. As it's a non-interacting system, we can calculate any observable using the this correlation two-point correlation matrix. So we have the evolution of the correlation matrix is it's unitary evolution. So C0 is the initial correlation matrix, and it is evolved by the full non-interacting single particle Hamiltonian H. And the initial condition C0 is the system is filled, so this is the delta Ij for the system, and the bath is empty, so 0 for the reservoir. So we have calculated various observable like particle density, current, particle number fluctuation, entanglement entropy. So this is a pure initial state, so entanglement entropy and the von Neumann entropy are same. So this is the entanglement entropy. Also, we can calculate the cumulant generating function for the full counting statistics. So one thing is notable that particle density current, this involves the elements of the correlation matrix, whereas the particle number fluctuation, entanglement entropy or full counting statistics, this involves the eigenvalues of correlation matrix. So xi L, this is the eigenvalues of the correlation matrix. So we can also calculate the dynamics of various observables using the generalized hydrodynamics. So we can think the system is like a gas of quasi-particles with fixed momentum k, and we can look at the evolution of the phase space density for free fermionic case. So it is just the Euler's equation, it follows this Euler equation where sin k is the group velocity for the quasi-particles. And the solution, if there is no defect and no defect and no finite system size, then the solution is nothing but this. Like only the position of the quasi-particle gets boosted by t into the group velocity sin k. So position is shifted by this. And for this setup, we have this initial condition, this is the initial condition, this is the phase space plot for that. So the system is filled with the quasi-particle, whereas the bath is empty. Now we can solve in presence of the finite wall and the defect, we can solve this Euler equation, and it gives the phase space density at any given time as a sum of various multiple number of reflections. So, and we can, because now we have the finite wall and the defect. So the quasi-particles, as the evolution progresses, the quasi-particles will do like multiple reflections. So the solution will have sum of many reflections. So this is the solution. And these are the plots for the this phase space density for different times, which obey these solutions. So now we have this phase space density at any given time in hand. So using generalized hydrodynamics, we can calculate different observables. So we can calculate particle density. This is the form of that. We have to integrate the phase space density with K. So we'll get the particle density. We can calculate current. So we can calculate total number of particles in the system, and we can look at the change of the total number of particles with time. So that will give the current. And we can also calculate the hydrodynamic entropy. It's like the von Neumann entropy in the exact numerics, but now here we have the phase space density instead of eigenvalues of correlation matrix, and we have integration over dx and dk. And also we have, for this work, we have no idea, so how to give the hydrodynamic description of this particle number fluctuation or full counting statistics for all the time. So this is the plot for the matching of the density, particle density and the current with exact numerics and hydrodynamics. You can see that hydrodynamics really captures the like particle density of current for all time. It misses some of the like oscillation, but in a coarse-grained manner, it really captures so well the hydrodynamics thing. Next, we plot the entropy as dynamics for like exact microscopic. The blue thing is the exact microscopic, and we have also calculated using the hydrodynamics for the reservoir part and for the system part. So it seems that for the system part, so for all time, this entropy really matches well with the exact numerics, whereas for the reservoir part, it matches up to some time and then it deviates. And the particle number fluctuation from the exact numerics, so it also gives a similar feature like the this entanglement entropy dynamics. So here, this entanglement entropy and particle number fluctuation shows this kind of dynamics, and this is known as the page curve like dynamics, because in the context of this evaporation of black hole, Page has shown that this the entanglement dynamics of black hole and the rest of the and the radiation is also shows this kind of dynamics, like initially starts from 0, goes to a maximum, and then goes again to 0. So this is known as the page curve like dynamics. So, here we can see the system hydrodynamic entropy captures the full page curve dynamics, where the reservoir entropy fails to reproduce the full page curve after some time. And here we have only shown the result for conformal defect, but this is true for any point defect. And from the hydrodynamics, we can find analytically long time behaviors, which we may not find from the exact numerics. So what next in the future, like work we have, like here we have only give the like hydrodynamic description for the pure state, but can we extend this for more general initial states? And can we find more rigorously why the system hydrodynamic entropy captures the full entanglement dynamics very well, but not reservoir hydrodynamic entropy? And can we provide the hydrodynamic description for full counting statistics for all times? So then in the next works, we have given the answer of all these the question, like yes, we can extend this for more general initial states. So if the system is not in the pure state, if it is in the thermal state also, like then also we can give the hydrodynamic description, and also we can now rigorously find why this hydrodynamic entropy captures the like exact microscopics very well. So we can actually from hydrodynamics we can give the like okay. Okay, so yeah. Okay, so I have result from the next work party. So I'd like to thank Atharva Man from the PhD student from ICTS, Manas, David Hughes, and Abhishek. Thanks.